All right, so I'm getting my sections mixed up a little bit, so I think I know where we left off, which was we kind of went through Excel examples of how we do differences in sample means. So we'll do differences in sample proportions today. One thing I wanted to mention is those second exams are all graded. I'm almost done with the Excels. I've got about, I think, 8 left. So for most of you, your third Excel assignment should be graded and it's kind of incorporated into your grade. For the rest of you, I'll be kind of getting those together here. The rest of the day, I should have them all graded by the end of the day. So one thing that I kind of did was I took the original exam scores. So actually, I'll upload I'll kind of put back in there exam 1. I'm not sure why it's not showing up here on the assignments. But I have your first and second exams, and then I kind of determined what the minimum kind of was and the maximum was, so your highest and your lowest. I then kind of factored that, weighted those according to the syllabus. So the highest exam, I weighted 30%, lowest 20. So the only kind of remaining 10% of the grade in the class, well, I mean, we've got a couple more of the assignments that are kind of factoring in here, but the only exam left will be kind of worth 10%. Now, obviously, if you do the best on the final exam, that becomes your highest, and the highest falls to your middle, the lowest will fall, becomes the third lowest. So things still could change quite a bit, kind of depending on what you score in that final exam. But currently, I'm assuming that the first 2 exams will be your best 2. If you didn't do as well, then this is kind of like a worst case scenario, kind of having them weighted the most. But given where we're at in the class, this is kind of, the best you can kind of get an idea of where your grade's going to be at once you take the final. Okay. Any questions on this? And then every other category is weighted 10%, kind of Learn Smarts, Excels, Connects, and your online quizzes. And then these are just kind of things that haven't been factored into the grade yet. So that 4th Connect assignment hasn't been due. This one I'll move down after class today because it was due before we started, kind of that Learn Smart, just getting that kind of read, and then that additional practice, okay? Any questions for me kind of at this point? And overall, I didn't talk about the exam Thursday, did I? No, okay. No, because I would have been the day after you guys got done. So the averages were pretty good. Like the mean and the median were right above a 75, and I think the median was a little bit higher, like a 77, 78. I don't remember the exact kind of decimal, but so it's where I like to see kind of the middle of the exams be. When I was grading in with the short answer portion, overall pretty good, especially given that hypothesis testing was kind of something we had done right before the exam. Looking at some of the Excels, a lot of them look good, and a lot of them look like you have never watched a video or showed up in class because you're using things that I've never done, right? And I've said, on these Excel assignments, everything that you should have to do on the assignments, we've done something in class, or at least, almost identical to it in terms of the actual way in which you would kind of, create a confidence interval or do hypothesis testing. So kind of a mixed bag on those. Hopefully moving forward, anytime we do something in Excel, because we will be doing kind of, we did some stuff last class, we'll do some today, and we'll do some this Thursday. That will all kind of be for the final Excel assignment, which I'll post after class today. So once we get done with today's class, you could probably get through about 2/3 of that assignment. And then kind of after Thursday, you should have everything you need, or might be missing just a little bit to get through the entire Excel assignment. So they'll be posted in kind of after class today and due kind of 2 weeks from today. Okay. Any other questions before we get going here? All right, so what we left off with was kind of thinking about, I can look at the difference in sample means, but I can also look at the difference in sample proportions. So I'm just going to kind of jump into this here. Really, the steps are similar. When we were looking at the difference in sample means, and actually switch this over here. Just a kind of a reminder of where we left off. So if we're building confidence intervals for the difference in sample means, it looks something like this, right? So it's kind of a reference to what we did last Thursday. So we had each group's population variance divided by that group's sample size, where this represented the standard deviation of the difference in my sample means. Let's see if I can go in here a little bit. There we go. So now what we're going to do is we're thinking about, okay, I want to know where the true difference in sample proportions is, right? We kind of said last class, we can think about this almost as the sample difference. It's supposed to be a capital D, and it almost looks like a D. Well, we can find the sample difference between sample proportions as well. Just like with one population, I'm using proportions, so I know I can use that standard normal, or that Z table. And then here, now what I multiply is the standard deviation of the statistic I'm interested in. So now it will be the standard deviation of the difference in sample proportions. Now what that's going to be, if we kind of think about here, before all I was doing was, here was the variance of my sample proportions, and then I added that to the variance of my this was the variance of my sample means, and I added that to the variance of the sample means on my other group, right? So I'm going to do the exact same thing here. But when I'm dealing with a proportion, I don't have a kind of given population variance, but I know it's going to be that sample proportion times 1 minus that sample proportion. And then if I'm looking at kind of the sample, I have to then divide by my sample size. And I'll add that, right? Add both groups' variances together, right, underneath this square root. So this didn't quite go out far enough, right? So now this represents the standard deviation of the difference in my sample proportions. Same idea, right? To get that standard deviation for the difference, I'm just adding the standard deviation, to get the variance of the difference, I'm just adding the variance of each sample together. And then I want this standard deviation, so I have to take the square root, okay? But it's really kind of the same sort of setup. It's just a slightly different statistic. Right, a sample proportion instead of a sample mean. So we know that we can use this for our confidence intervals. Like once we have this, really it's the same process as what we were doing with sample means, right? We look up the z-scores the same way. It's just kind of, a slightly different equation where we're plugging our values in. So we'll wait for the slides to switch over here in class. So that's where these equations came from. Right, my lower and upper bound equation here for the difference in sample proportions. Oops. So we're going to work through an example. Okay. So let's say we have kind of this survey. We've got a reported amount of 84% of people favor healthcare coverage for everyone, and then in 2010, 82% favor healthcare coverage for everyone. We've got slightly different sample sizes in those 2 years, and I want to build a 99% confidence interval. So first off, I've got kind of thinking about 2 sample proportions, one from 2010, one from 2011. Right? And I'll blow this up here in a second. I'm just going to get this down so I don't have to keep switching back to the slides. I've got my sample size in 2011 was what? That's the one that's 607. And then the sample size in 2010, 600. At the 99% confidence level, my alpha is going to be what? So alpha is the area outside my confidence interval, but in decimal form. So if I want the 99% confidence interval, alpha would be, just 0.01. Right? So that's kind of my setup, right? Well, once I have that information down, I've got my formula. I've got everything I need, my sample proportions, my sample sizes. I know alpha. I just need to look up that Z value. I need to look up that Z value, right, for this alpha. So what I'm going to do, and I'll come back to this in 1 second. When I'm thinking about looking up these Z values, I can think about, well, I've got this distribution, and I want to find this value such that there's alpha over 2 kind of on each side of my interval. Right? Well, if my alpha is 0.01, then the area that I actually want is 0.05 kind of on either side. Okay? So what Z values, kind of think about, would give that to me? Or how many standard deviations away do I want to go? So we've got the area in the tail. We just go to our standard normal table. Okay. So I want 0.005, so I'm going to go down here, hunting for it. Looks like it's in between these two values right here. So negative 2.57 and negative 2.58. So we'll use the higher of the two, 2.58. But remember, I just found negative 2.58. Well, that's the number of standard deviations below I want to go to get my lower bound. Well, that positive and negative sign for the upper and lower bound, right, that's already built into our equation. So when I found negative 2.58 for confidence intervals, I need to remember, well, I actually just wanted, to know the value, so I don't really need the negative sign here. It's already built into my equation. But once I have this 2.58, it's really just a matter of plugging all those values in, right? Now, one thing I could do is calculate this first, like do the intermediate step so that I could find what that standard deviation is and then just plug in that one value, similar to what we did for one population examples and for when we were doing the kind of difference in sample means here. But I can do it all at one time if I really want to. Okay. So, excuse me. All right, I've got all the information I need. I found that z-score, right? And here I got it a little bit more exact. I'll show you how I did that in just a second. But really at that point, it's just a matter of plugging everything in, right? Plugging in our sample proportions, sample sizes, and that z value. Okay. So, I don't know, at this point, it's like I said, just getting it entered into our calculator correctly. And one thing that can assist with that is maybe calculating that standard deviation of the difference in sample proportions ahead of time. Okay. If you don't want to do that, you can do it all in one line like I have right here, but very similar to what we did with differences in sample means. It's not a whole lot new going on here. Now, how did I find this z-score out to the third decimal without using Excel? Whoops. Well, not Excel. If I use the student t distribution, remember the last row shows me the standard normal values. It's kind of a way to like cheat by only using that student t. So if I go up here, what's the area that I wanted in the tail? 0.005, right, or 0.01 divided by 2. So if I go down here to that last row, which represents the standard normal distribution values, that's how I got 2.576, the exact, right? I wasn't kind of constrained to being in 2 decimals. Okay. Any questions on this example before we keep moving forward? So, if I'm thinking about, if I want to make a statement about have people become kind of more in favor of healthcare coverage for everyone, well, if I look at my confidence interval here, I've got what, negative 0.03 to 0.07. So if I think about what I've got, 0.036 to what, 0.076. So what this is saying is that the true difference between 2011 and 2010, right? That true difference could be a negative value. It could be a positive value. If it's positive, well, that would mean that 2011 is greater, right? If it's negative, well, the only way this difference is negative is if 2010 is greater, or one of the values in this range is 0. If the difference is 0, that means that proportions could be exactly the same between the 2 years. So anytime I have this confidence interval that crosses over 0, I can't really say much because the true difference could be negative, could be positive. In fact, it could even be 0. Could be that there's no difference between those 2 years. Okay? If we had one maybe that was like, I don't know, 0.05 to 0.08 or something. Well, this is a little more interesting because now the true difference could only be positive values. So now at this confidence level, I could say that, the difference is positive or that they've increased. This, favorable views of healthcare coverage for everyone has increased if this was the confidence interval. But it wasn't, so I can't say anything. Okay? At least not at the 99% level. Any questions or clarifications on that? Okay. We're okay with that? So, we could go through different examples. Here I've got a second example. I think for the sake of kind of where I think we'll end today and sake of time, I probably won't go through this one in full detail because it's really going to be exactly what we just did, right? If I want the 99% confidence interval, what's the Z value that I'm going to need once I go to my confidence interval equation? Well, if it's a 99% level, what's alpha? We did it last problem, 0.01. So I'm still going to find the Z, so it gives me 0.01 over 2 or 0.005. I'm still using the standard normal distribution, so that value is not going to change. I'm just going to be using that same, wherever it was, 2.58. The only thing that's changed are my sample proportions, right? I'm looking at a different question now, and it's whether or not people have unfavorable views of the Affordable Health Care Act. Right? So I've got kind of two different sample proportions. That's the only thing that's going to change in this example. So it's really just a matter of getting our values plugged in here correctly. So we still see here, if I wanted to make a statement about have views of the Affordable Care Act changed, well, 0 is included in my confidence interval. So once again, I really can't say much, right? That difference could be negative, right? Could be positive, or it could be 0. If the difference is 0, it means the proportion is identical between the 2 years. So it's a very similar example. But one of the reasons I always use this is to kind of show some like survey stuff that we talked a little bit about before, just the way you ask a question. So notice when they're asking about the Affordable Care Act, right, you've got about 50-50 kind of whether or not people like it or not. But when you asked about what the Affordable Care Act was meant to do, which is ensure healthcare coverage for everyone, you get about 80% of people in favor of that, right? So it's interesting if you name the policy as opposed to what the policy is trying to do, you can get very different results. Okay, so like I said, I won't waste too much time on that because it's really the same procedure. We'll see an example in Excel as well where I'll walk through a little bit more. I think it'll kind of type something out like this. So if we can do confidence intervals, just like for the difference in sample means, we can also do hypothesis testing, right? So the hypothesis test for a proportion, right? We know that the kind of variance of each sample proportion is going to look a little bit different. Okay? Excuse me. So similar to when we talked about sample means, if I want to find the difference in sample proportions, my test statistical equation is going to look a little bit different. So one thing that's kind of an issue here is when I was using population variances, so before, when I was using population variances for the mean examples to calculate that standard deviation, that was fine. They're not impacted by sample size. The issue is, actually, I think I've got it right here. The issue is when I look at the confidence interval equation for the difference in proportions, notice my variance, right, depends on the sample statistic I found, okay? And because it depends on the sample statistic I found, when I go to plug in my standard deviation of the difference in those sample proportions, it doesn't work out to simply be this. If I just use this as my standard deviation when I'm doing hypothesis testing, then this value that I'm coming up with wouldn't be a Z statistic. It wouldn't be coming from a standard normal distribution. So we have a slightly different equation, and I kind of break it down into this intermediate step so that, I don't plug, imagine if I plug this equation into where P bar is, this denominator would look like a mess. But really what this is trying to do is it's trying to create a weight, right? If I have one sample that has a higher sample size than the other, well, these sample proportions, right, using those to calculate the variance is going to have a little bit more of an effect if I have a larger sample size. So kind of notice if you really rewrote this, it's taking like sample size 1 over the sum of the 2 samples. So it's kind of like weighting, right? Essentially, this is like a weighted, using weights to weight the different sample proportions by, a different amount. So it's a little bit different of a test statistic, but other than that, our hypothesis testing has not changed at all. So you notice we're taking the statistic we're interested in, we're subtracting the assumed true value of that statistic. Now I said here, I'm always going to use 0. The assumed true difference is either greater than, less than, or not equal to 0. And now if you remember, it's a little bit different of a calculation, but what this denominator represents is really supposed to be the standard deviation of the difference in those sample proportions. Okay? So it's still representing kind of a similar thing to all the other Z values, all the other test statistics we've looked at. this denominator represents the standard deviation of the statistic that I'm looking at, so the standard deviation of the difference in sample proportions. But once I know that this is my test statistic equation, like once I have this to be able to use this, the steps, this is the exact same slide that I've shown you quite a few times now, where nothing changes. We identify the null alternative. We need to know our alpha. Knowing the alpha and whether or not we have a left, right, or two-tailed test, we find a critical value. The only step that's a little different is we have a new test statistic equation, but it's still coming from a z or a standard normal distribution of the z tables. And then we just compare our test statistic to see if it's in our rejection region. We could also do the p-value approach, right? Use alpha to find the p-value, then compare the p-value, or sorry, use the test statistic to find the p-value, and then compare the p-value to alpha. Okay. So the steps haven't changed at all. It's just this test statistic equation will look a little different. So let's work through an example here. So I've got, prior to the last election, so I think this Rasmussen poll, I did a bunch of this now, I can't remember. I think it was supposed to be one of the ones that predicted the 2016 election correctly. So they had 1,500 people. They found 49% of people planning to vote for Biden and 47% planning to vote for Trump. And I wanted to test the proposition that Biden will receive more votes than Trump. Okay, so I want to know, will Biden receive more votes than Trump? So I'm thinking about my null alternative hypothesis here. When we have these difference ones, it's a little bit trickier, right? So eventually what we're going to want is something that looks like this, where we have the difference, right? And we've either said that it's greater than 0 or less than 0 or not equal to 0, right? Well, if I want to test for whether or not the proportion of votes for Biden will be greater than the proportion of votes for Trump, this is kind of what I said in words, right? Well, another thing that has to be true is if Biden has a greater proportion of the votes than Trump, then the difference between Biden and Trump would have to be what? Yeah, greater than 0, right? If I subtract this from both sides, I'd have this, which represents my difference. And I'd be saying, is that difference greater than 0? Okay? So that's my alternative hypothesis. Right? It's a little bit trickier just because of the way that we usually talk. We say, well, is the proportion of Biden votes greater than the proportion of Trump votes? We usually would say, is the difference between the candidates' votes positive? We just usually don't talk like that. And so it's a little bit tricky to identify what you want to find. But once you know what you want to find, that's your alternative hypothesis, which means the null is the exact opposite. So I assume the difference is negative, right, or equal to 0, which is really saying I am assuming they get the same amount of votes or that Trump will get more. Okay? That's kind of what my null hypothesis is here. From there, right, it's a matter of identifying what we were given in the problem. So I believe kind of the sample for Biden was what, 0.49. Sample proportion for Trump was 0.47. Our sample size is kind of a unique one where it's coming from the same survey. So the sample sizes are actually the same, which is that 1,500. Well, at this point, I have everything that I need, right, to plug into my test statistics. So I've got my sample proportions, 2 sample sizes, and I've got this assumed true difference of 0. Okay? Well, that's everything that I needed. So if I go back and I look at this, actually, I think I have the equation on the next slide. Oh, no, I don't. I skipped critical value. So I'm going to go to the test statistic here real quick, and we'll go back. So remember, here's my equations for that test statistic. Calculating the test statistic, once you identify the right one, it's really just a matter of plugging those values into our formulas. So plug in your sample proportions right here. Plug in your sample sizes. Notice this one, because the sample sizes are the same, when I kind of weight this, I'm just going to get the average if I have the sample sizes that are the same, because they're kind of both should be weighted equally if they have the same sample size. So that works out to be just the average of my 2 sample proportions, P bar. I'll then plug that into the denominator, plug in my sample sizes, plug in my sample proportions. That assumed true difference, like this equation really becomes easier because I'm telling you I'm always going to use 0 there. So if I subtract 0, nothing should change. So once I do that, I'll get my test statistic of about 1.097. So we'll kind of remember this. Actually, I'm going to write it down next to me for when we go back to the dot cam. So 1.097. Well, what would my critical value be? Well, what type of, well, I'm already showing you. So what type of tail test did we have here with a null alternative? Well, I've got a greater than sign. So that's a greater than or a right-tailed test. Okay. So when I'm thinking about this, when I'm looking for my critical value, remember, whichever distribution I'm using, that's what my critical value is. So if I've got proportions, I use that standard normal distribution. I've got a right-tailed test, so I want the critical value that gives me alpha in this right tail. Okay. I believe this was the 99% confidence level, so alpha would be 0.01. Now, I know that my critical values for a right tail test should be what? Is there anything I can say about right tail test critical values? Think about, yeah, they're positive, right? Because remember, the standard normal distribution has a mean of 0. Okay. So I know the area to the right of 0 is 0.5. So if I'm looking up these small alpha values as the area in my tail, well, I know my critical value has to be to the right of that mean. Well, the mean's 0, so the critical values have to be positive, right? So left-tailed test, negative critical values, right-tailed test, positive. And we'll do a two-tailed test example here in a little bit where we see that we have kind of a pair of critical values. That was one kind of common mistake I saw on the short answer. Was a lot of people, even if they identified the correct value, they, for a two-tailed test, you have to mention that there's a pair of critical values, right? One positive, one negative. But here we've got a right-tailed test. So I can go about looking up this critical value in two ways. The first is I've got an alpha of 0.01 in the upper right tail. So when I go to the table, it's always looking at the area to the left. So if I just look up alpha, it's going to be looking at the left side of that distribution. It'll give me the same value. So I could get 0.01 in that lower left tail. It's just, it'll be this value, but negative. So I can look up alpha, find the corresponding z value, and just remember it's a right-tailed test, so it's just positive. Or I could say, well, anytime I go to that standard normal table, it's looking at the area to the left. If the area to the right of this value I want to find is 0.01, what would the area to the left be? The area under the curve is 1. So the area to the right is 0.01. The area to the left would be, yeah, just 0.99, right? So I could look up 0.99 and I get the same value. So I'll show you kind of both those ways, right? So first of all, I think we look at the critical values. Well, I've got it identified here, but they were all positive, so I couldn't rule anything out. So we go to that z table, right? And I try to look up 0.01. Looks like it's in between these two. So negative 2.32 and negative 2.33. So I'll take the higher of the two in absolute value. So negative 2.33. It's a right-tailed test. Remember, if I just look up alpha, for a right-tailed test, I have to remember, oh yeah, that's looking at the kind of lower left tail. I'm looking at the upper right tail, so it's 2.33. It's positive. Now, I also said you could have looked up 0.99. So if I try to find 0.99 down here, it's in between these two. So 2.32 and 2.33. Sure enough, I find that same value of 2.33. Okay. And I think in the slides, I use the cheating, quote unquote, method, which is that if I want alpha total in the tail, I could look that up on my student T table. I wanted 0.01 in that tail. And then just remember the last row shows me the standard normal values. So 2.326, right? Which is in between 2.32 and 2.33, right? It's just a little bit more exact. So any of those methods are fine for finding what that critical value is, right? Like if I'm asking this on an exam or something, like I'll accept 2.326 or 2.33, right? No matter which kind of method you use. Okay. You can really use it any time in the sense that, so whenever I'm working in reverse or inverse, and I know the area in the tail, but I want to find what a z value would give that to me, I can use my student T table. Now the issue is, I can only look up 6 different areas in the tail. Now, it's not a big issue with confidence intervals and hypothesis testing because we typically use the same alphas, right? We're typically looking for the same areas in the tail. If we had, some slightly different alpha values, then things get a little bit more complicated because this isn't a complete table. But anytime you're looking up kind of some of these conventional areas in the tail, you can always use that student T. You just have to remember, I can only use the last row if I should be using a standard normal distribution, because that's what these values represent. Does that make sense?
Yeah.
Any other questions? I'll work through a couple different methods there. Okay, so we found that critical value of 2.326. So what? 2.326. So you kind of think about my rejection regions, this area to the right. If I go back and remind myself, the test statistic I found was 1.09. So if I'm thinking about where that test statistic is, or that Z statistic, since it's coming from a standard normal distribution, it's not in my rejection region. So I would say I failed to reject at the 99% level. Okay. Any questions on this? So if I wanted to find the area to the right of my test statistic, my Z statistic for a right-tailed test, this would represent my p-value. The probability I saw something as far away from the assumed true difference as I did, or anything even further. Okay? So if I want to find the area to the right of 1.097, I can use my standard normal table. So what I'm going to do, I have something out to the third decimal, so I have to round it to the second decimal, so it's going to be 1.10 if I round it. 1.097 is 1.10. So go to my Z tables, 1.10, 0.8643. Now remember, the table tells me the area to the left. I wanted the area to the right, so what do I have to do? Subtract that from 1, right? So we get what, 0.1357. Okay, so here's my p-value, okay? 0.1357. Any questions on that? So if I want to make the rejection decision here, well, this is where when if I use the p-value approach, it's a lot, I don't know, I think it's a little bit easier to make rejections at different levels pretty quickly. So I only reject if the p-value is less than the alpha that I've set, okay? Well, here I believe the alpha we had was 0.01. So is 0.1357 less than 0.01? No, so I fail to reject. Is it less than 0.05? No, so I fail to reject. Is it less than 0.01? No, sorry, not 0.01. 0.1. Not quite, so I fail to reject. Sorry, this is 0.10 if you're kind of writing that in. Okay. Any questions? So we make the same rejection decision no matter which approach we used, right? Whether or not we use the critical value approach where the test statistic wasn't in the rejection region, or we use the p-value approach and see the p-value is not less than alpha. Okay. Any questions on this? Okay, like I said, we're still going to hammer on these hypothesis testing questions, so hopefully they're getting a little bit easier. So really, what are we saying? Well, we did find evidence here, right? If I think about the sample difference I found, 0.49 minus 0.47, I did find a sample difference that was positive, or that Biden would get more votes. However, if I'm trying to make a rejection of the null, well, my null was that difference is less than or equal to 0. So I found evidence that goes against the null, but does it go against it enough, right? Because I could have just had, kind of skewed samples, right, that gave me the sample proportion for Biden was a little bit higher and the sample proportion for Trump was a little bit lower than what the true population proportion is, right? I really don't know. So once I go through all this, I find, thinking about that p-value, which I don't know if I have this on the slide. So let me pop this here. So that p-value is telling me the probability that I saw the difference that I did, if in fact the null was true, was about a 13% chance. Well, that didn't meet my threshold that I set of 0.01. In fact, it doesn't even meet the threshold of 0.1. But that being said, it's pretty close, right? So I failed to reject the null here, but this is where, you know, in practice, like once you go out there and start working or when you're trying to do something like this, you're going to look at this and say, okay, yeah, I failed to reject at the low, you know, that 90% level, right? The 10% significance or the 90% confidence level. But I mean, if you lower that just a little bit, right? Maybe you lower this down to, you know, an alpha of 0.14 or the 86% confidence level. Well, now I could reject it, right? And I could say that Biden's going to get a higher number of votes. So, you know, it's, you know, not that far away. We can't reject here, but we could have made a pretty good prediction about what the outcome of the election was going to be, at least in terms of the popular vote, right, nationally. Okay. Any questions on this? Okay. All right. So I worked through this problem earlier, and we built a confidence interval. So I want to connect confidence intervals to hypothesis testing when we have these kind of two population examples. Sorry, yeah, two population differences. So I've got the same setup as that confidence interval equation from earlier. 84% of people were in favor of you know, healthcare coverage for everyone in 2011, 82% in 2010. And I want to test whether or not they have different views between those 2 years. So what I'm thinking about there is if I have different views, is something like this. If I can get the paper off. All right, so what I want to test for is whether or not that difference is, well, if I'm thinking about different views, I'm just saying, is the difference between them anything other than 0, or is it not equal to 0? So similar to the one population examples, anytime I see this word different from, different than, when I have these difference in proportions or difference in means, that word different should be thinking about a not equal to sign in the alternative hypothesis, right? Just want to test for whether or not the difference between these two is anything other than 0. So I assume the opposite for the null, which is that that difference actually is 0, that they're exactly the same, that views haven't changed at all. Excuse me. So I've got what type of tailed test here? Two-tailed, right? So automatically when I'm thinking about critical values, I should be thinking about there's a pair of critical values. So why? Well, if I think about what I'm doing with a two-tailed test, right? Still using that standard normal distribution, I'm trying to find the value that gives me alpha total in the tails. Well, I have a tail on each side now, so there's alpha over 2 in each tail, so I'm looking for the critical value that gives me alpha over 2 in each tail. Well, I need two values then, one negative, one positive. So once I find that, you know, then my rejection region would be kind of the areas going into the tail, right? So if I see a test statistic here or a test statistic here, I could reject, right? Evidence on either side goes against the null. So I don't even remember what the alpha level was here. Let's say it's 0.01, okay? So 0.01 divided by 2 is 0.005. I feel like we've been through this before, right? If the area I want in the tail is 0.005, you know, I can use that student t-table to cheat a little bit. I want the area of 0.005. I'll just use that last row of the student t-table. It gives me the standard normal value, 2.576. Okay. So it's the exact same value we found before. If we go back to the earlier problem, if I can find where we had that. Here it is. It's really the exact same kind of setup as a confidence interval. So two-tailed tests are very similar to confidence intervals. So I'm going to find that same z value. This time I use the student t to kind of get it out to the third decimal, but it's the same value. Now what should be true is that for a confidence interval, any of these values could be the true difference. That's what the confidence interval is telling me. Any value in this range could be the true difference. So if I do a hypothesis test for any value in this range, I should fail to reject it, right? Because any value in this range could be the the true difference between these population proportions. So if I'm using that assumed true difference of 0, if my confidence interval includes it, then for a two-tailed test where evidence on either side matters, I should be failing to reject this. Okay. Now we can see if that's gonna hold or not, right? We can work through the rest of this problem, right? So we found what my pair of confidence intervals was negative and positive 2.576. The next thing I'm going to need is my test statistic. Excuse me. So if I'm looking at these values and I'm thinking about what my test statistic is going to be, I mean, one of these seems outrageous, right? So 42.7 would mean that the sample difference I found was 43 standard deviations almost away from that assumed true difference of 0. Okay. Well, that's very far. That seems like, you know, I found a sample difference of what? 0.84 minus 0.82, 0.02. I doubt that's going to be 43 standard deviations away. I know I've got kind of a high sample size here, but not that high. So, you know, I identify the things I need, my sample portions, my sample sizes. I've got my critical value, or my critical values, the pair of them. So I just use this equation for the test statistic. I plug in my sample sizes, plug in my sample proportions. P bar should be about 0.83. Right? So I'm rounding to the second decimal. I then plug in P bar here, plug in my sample sizes, my sample proportions. What's my assumed true difference? So if I go back to that normal alternative, the assumed difference here I'm using is 0. That's what we're always using in these examples, just to make it a little bit easier for us, okay? So once I plug everything in, I should get about 0.925, okay? So I've got a test statistic of about 0.925. Well, if I think about where this is going to fall, somewhere out here. So 0.925 is my Z statistic, or my test statistic. Nowhere close to my rejection region, so I failed to reject the null, which is what we said. You know, if I assume it's equal to 0, I should be failing to reject it, because based off of my confidence interval, that could be one of the possible values for the difference. 0 was in my confidence interval. Now, this doesn't quite work if you're doing one-tailed test, because now instead of alpha over 2 on each side, all of alphas in one tail, so it wouldn't have kind of the same, it wouldn't line up perfectly with the confidence intervals. For a two-tailed test, any value in your confidence interval you do a hypothesis test for, you should be failing to reject it. Now, you shouldn't have to like do both of these all the time. It's kind of different. Confidence intervals and hypothesis testing provide us with different useful information. The confidence interval allows us to, at one level of confidence, or at one alpha, be able to determine a wide variety of possible values that difference could be. Right? So it allows us to kind of, at the same level of confidence, look at all the possible values that we would be failing to reject as potential true differences in the populations. With hypothesis testing, it allows us to kind of look at whether or not, for one value, it allows us to see which levels could we reject or fail to reject that is or could in fact be the true difference, right? Because through hypothesis testing, we get this p-value or these critical values, we can very quickly check to see a bunch of, you know, we usually do 0.1, 0.05, and 0.01, but once I have that p-value, you know, before, just using it as an example, I think we had the p-value of 0.13 somewhere. Yeah, so I had 0.1357. What this is really saying is, well, for any alpha that's, you know, set below 0.1357, I actually fail to reject that this assumed true difference is in fact the difference, right? But I could reject at any alpha below this, right? So it kind of allows me to do a lot of different like rejections or failures to reject, but for just that same one value, which here is 0. Okay. So kind of different usefulness, but we can get similar things from them, and that's kind of why the two-tailed test lines up with that confidence interval. Okay. So where are we at on time here? All right. Okay. I didn't do that. Any questions on this before we kind of keep moving here? So I'm going to go back to that Excel file that we were working with on Thursday. So I believe we completed, right, or at least what I had saved, we had completed kind of all the way down, doing some hypothesis testing, doing some confidence intervals for the difference in sample means. Since we're doing proportions today, we're doing the exact same thing, but for proportions, right? So up here, I've looked at this variable, which is basically just so here's my southern schools. If the female undergraduate enrollment is greater than the male undergraduate enrollment, I put a 1. If it wasn't, right, if male undergraduate was greater than female, there was a 0. Okay. So a couple of you on the last Excel assignment, and I think there was some confusion in general, but I know that I mentioned this. Actually, I know I mentioned it more than once in class. If I want to find the sample proportion and I have a data set like this and it's just this 1, 0 variable, yeah, I could go through and count up the number of ones and then divide by the total number of observations. But that's really what that's what my average or calculating the mean would do for a 1, 0 variable, right? Because in that numerator, it's just going to add up all the values. Well, the zeros don't change anything. So the numerator is just going to be the number of schools that have more female than male students. And then if I divide by the number of observations, well, that's exactly how I find my proportion. This many out of this many. So using this average function in Excel for a 1, 0 variable will give you that sample proportion. We use the count function to find the sample size, right? This is kind of old stuff we've already done before. And then here I have my Midwest data on a different sheet. So I did the same thing where I calculated the sample proportion and sample size for this sample of Midwest schools. And then I showed you on Thursday, we can actually, how did I do this? I just went equal sign, selected a different sheet, selected on the cell that I wanted to kind of put in here, and then I've got it all on one sheet right in front of me, okay? So what we're gonna do here, we're gonna do a left-tailed test, right? I've got a less than sign in the alternative hypothesis. So I'm gonna do this left-tailed test. Oh, sorry, I jumped the gun. Let's do the confidence intervals first, my bad. So let's do this confidence intervals first. So the first thing I'm gonna need to do is, if we look at that confidence interval equation we were working with earlier, I'm gonna need to use Excel to find these z-values. So a couple of you, I had to take some points off on the last assignment because you looked these up manually. So on these Excel assignments, I don't want you to do things, I want you to be able to do everything in Excel, right? So you need to use a function in Excel that we've used to find what this z-score is. Well, I want the z-value, or the kind of z-score that's going to give me alpha over 2 on each side of my interval, or kind of in each tail. So I'm working in reverse, where I know the area in the tail, and I want Excel to tell me the z-value. So norm.s, because I'm dealing with proportions, I can use the standard normal distribution. Norm.s.inv is when I know the area in the tail I want, so alpha over 2, and I want Excel to give me the z-value that gives me that area in the tail. Now, similar to when we did this by hand, when Excel does this, alpha over 2, it's treating that as the area in the lower left tail. So it's going to give me a negative value. Well, in my upper and lower bound equation, that's already built in, right? So what I simply want to do is use the absolute value of that, okay? So now I've got my z-value. If I copy this down, it updates the alpha so that I can find the z-values for 3 different levels of confidence very quickly. Okay. Now here's where I would probably do an extra step, okay? I would probably up here find the standard deviation for the difference in sample proportions, okay? And what that is going to be this guy right here, right? So I'm going to just put this in a different cell. So go up here. It's probably going to not like this. I'm going to take the square root of my sample proportion times 1 minus my sample proportion divided by my sample size. And then I'm going to just want to make sure we can see this. Right. then I'm going to do the exact same thing and add in for the other sample. So take that sample proportion times 1 minus that sample proportion. It's not going to let me click on this cell here, but it's what? Divide by that group's sample size, right, which is in S5 here. So I'm just calculating this ahead of time, just so I don't have to do this all in one cell. You can do it all in one cell if you want, and I'll show you in a second what that looks like, right? But I could also calculate it up here. Okay? So now that I have that, I know that my lower bound will just be the statistic I'm interested in, which is the difference in my sample proportion. So here I phrase it as the Midwest minus the South, or difference between Midwest and South. So I'll take the Midwest sample proportion, subtract the South's sample proportion. That's where I'm centering my confidence interval around. I then need to subtract my margin of error to get my lower bound. So I subtract that Z value, right? That's the number of standard deviations away I want to go, times whatever that standard deviation is for the statistic I'm interested in, which in this case is the standard deviation of the difference in my sample proportions. Okay. So now that I have that, this should give me the lower bound, but I can get the other two lower bounds pretty quickly. Now the problem is going to be if I copy this down, well, it's updating these cell references. I don't want those to change. The only thing that changes for these different levels of confidence, is how many standard deviations out I need to go, or my Z value. So when I'm looking at this, the only cell reference I want to change when I copy this down is the Z value. So I'm going to freeze everything else. So Command T on a Mac and then F4 on a PC. So it's going to freeze everything that's not a Z value. Okay. Now when I copy this down, get my lower bounds pretty quick. How can I get my upper bounds quick? This is very similar to what we did with one population. I just copy, so Control C on my PC. I don't know what it is on a Mac, probably Command C. But I copy, hit Enter to get out of the cell, go over to my upper bound, paste it. The only thing that changes is I'm adding that margin of error. All right. Now that I do that, I can copy this one down, and these images are going to get in my way. So I'm going to move these over just a little bit so I can copy this down. And now we've got three confidence intervals built. Right? So I really only had to type it in one time. Right? I had to type it in for the lower bound. Once I froze the correct cell references, I could just copy it down and then copy and paste it over and change that negative to a positive sign where I'm adding instead of subtracting that margin of error to get my upper bound. Okay? I mean, it's very similar to what we did on Thursday with two difference in sample means. Really the only difference, notice I'm getting the same Z values. If I look at this format, it looks no different because the only thing that's really changing is I'm using sample proportions instead of sample means. And the difference is that the equation for the standard deviation of the difference in sample means, right? That's going to look a little bit different than the standard deviation for the difference in sample proportion. So that's really where the only difference was. Okay. Now, I don't know if I have it open, so let me open it here real quick. If you look at the completed file, and after today's class, I'll get what we worked on in class posted and call it, two population HT in class work, because we did a couple things that aren't in this completed file. We did things a little bit differently. But if I look here, what I did in the completed file, I put it all in one cell, and you can just kind of see, this just looks like a lot, and it's hard to trace down errors. And it's hard to figure, I can look at this and not realize I have an extra parenthesis so that's, I don't know. That's why I would calculate the intermediate value first. Just makes it a little bit easier. Okay? And it kind of, I think, lets you think of what we're doing a little bit more correctly. Okay? Any questions for me on this? All right, so we've got our confidence intervals. The next thing we're going to do is some hypothesis testing. So we're going to come over here. I'm going to delete some stuff right away. So I'm going to delete, I'm going to delete the p-value. I'm going to delete this right here. Okay. Let me think where I want to end the class before I go too deep into this. So if we do, okay, should be fine. So if I wanted to do some hypothesis testing, and I'm going to use this null alternative here. So just to be kind of clear, let's move this over so it looks like it goes more with this example. All right, I'm going to delete these, put a 0 in here, okay? And actually, I'm going to have to change this because I moved it. So now this cell would be right there. You don't have to change that part if you don't want it to. I might show you something before we end class. So I've got my z-stat, my test statistic. And really, how did I get this? I was just going back to, let's see where it was at, here. And I was just calculating p-bar in a cell and then calculating my test statistic. So I was just using Excel to be my calculator here, right? I mean, there's no built, unfortunately, they could do one, but unfortunately in Excel, there's no built-in function to calculate your test statistic, right? As we'll kind of see on Thursday, there is a built-in formula that calculates the test statistic and then spits out the p-value at you, but unfortunately there's nothing that just gives you the test statistic. Okay? So I have to enter that equation into Excel manually, basically. But I've got all the things that I needed, all the values in Excel, so it's just a matter of clicking on the cells where those values are. So I've got my test statistic. How can I find my p-value? Well, remember, we've got a left-tailed test. My p-value is going to be if I'm thinking about this left-tailed test, I'm using the standard normal distribution because I got proportions. I found my test statistic, which was what, negative 1.48. Okay. The p-value for the left-tailed test would just be the area to the left of my test statistic, or the probability I saw something as far away from the assumed true difference that I did, or something even further away that goes against the null. Right? That's the definition of my p-value. So I can find this. If I looked up negative 1.48 on the standard normal table, it would tell me the area to the left, and I could find the p-value. I can also do it in Excel, not be limited to 2 decimals. I now know the z value, and I want the area in the tail, so that's the norm.s.dis, right? Use the standard normal distribution, look up a z value, and tell me the area to the left of it, right? Or the probability I saw something this many standard deviations away from the assumed true difference, or even further. So I've got my test statistic. We said we always use comma 1 here. So some of you, I saw in problem 1 of the last Excel, we're using a 0 in here. And I think the thought process is that it tells you the area to the left if you put a 0 in. That's not what it does. And I know that I said that that's not what it does. So prior to today. So you should always be using a 1 here when you're using really any dist function we're using, any dot dist, always put a 1 there as that last argument. Okay. Excuse me. So that should give me my p-value. Right? So it's about 0.069. Okay. So about 0.07. That'd be easy to think about. So I've got my p-value. Very quickly, what levels can I reject at here? If I'm thinking about my rejection decisions, am I going to reject at an alpha of 0.1? So my rejection decision, I only reject if the p-value is less than alpha. Right? So if I look here, what will my rejection decision be at the alpha of 0.1? Yeah, 0.07 is less than 0.1, so I'd reject. Well, I don't want to do that. I hate when Excel's trying to be helpful. Okay. Can I reject at 0.05? Not quite less than 0.05, so I'd fail to reject there. Well, if I'm not less than 0.05, I sure as hell can't be less than 0.01, so I'm going to fail to reject there as well. Now that's just quick and easy using my eyes, right? So I'll show you another method that we could use to make these rejection decisions, and also the different approach. We'll use the critical value approach, right? So my critical values are going to be the value, right? So this would be my critical value that gives me alpha in that lower left tail. So I now am going to know the area in the tail, and I want to find the z value that gives that to me. So instead of norm.s.dist, I'm working in reverse So it might help you think about, we're going to do norm.s dot INV, or kind of the inverse, right? So now I know the area in the tail I want is just alpha. And actually, it's the area I want in the lower left tail. So it's going to give me, the value will be negative, which is what I want for my left tail test. So here I've got my critical value. I then copy that down. There's my critical values for these 3 different alpha levels. Okay. Now, what we're doing with critical values is we could create 3 rejection regions. So, and I could have drawn this up here, but I think it's just going to get messy. So 3 critical values we found were what? Negative 2.32. Here's the rejection region. Negative 1.644. Here's the rejection region. And then negative 1.28 something, 281. Here's the rejection region. These correspond to the 10, 5, and 1% significance levels. So all I'm going to do is see, okay, where does that test statistic fall, right? So where does my test statistic kind of get plotted here? Well, it's negative 1.48, so it would be, I almost drew this exactly. Drew this pretty good, right? Negative 1.48, or my z statistic or my test statistic would fall right here. So I can reject at the 10% level because I'm in the rejection region. I fail to reject at the 5, and I fail to reject at the 1. Now, if I write this out like this, maybe this is a good way kind of visually to remember. Notice my test statistic is just below the critical value at the 5% level. Well, what was my p-value? My p-value was 0.069. Well, notice that p-value is going to be kind of, right? It's going to lead to me rejecting. If I compare that to 0.05, I was a little bit closer there. So it's almost like the test statistic, kind of where it's plotted, visually gives you an idea about kind of where the p-value would be plotted as well, right? If I could write every single z value down here on the x-axis, underneath it I could write the corresponding area to the left, which really is just my p-value and my alphas. Right? So just kind of comparing 2 different sides of the same coin, really. Any questions? Also, that what I just said made no sense. But it's 2 sides of the same coin. No, it's like you're just comparing kind of different axes here. Right? You can almost think about that way. Comparing 2 sides of the same coin. All right. Any questions on that before we keep moving? Anything that I have kind of here in Excel? Want to see a different cell again? Okay. So what we're going to do now is, so when we're thinking about this visually, it's a lot easier to use the critical value approach because you can kind of see where that rejection region is. But the other thing that we said we can always use is if the absolute value of my test statistic is greater than the absolute value of my critical value, then I reject, right? And really this just comes from the visual, right? So notice here, the reason why we take the absolute value is because here a larger negative value is actually less, right? But we want to make sure this applies to any type of tail test, left, right, or two-tailed. So if we take the absolute value, or think about, is my test statistic larger in absolute value than my critical value, right? Or is it more extreme? Well, then it would be in the rejection region and I should reject. So I can use this to kind of make my rejection decisions in Excel and kind of have it built in just in case, like, I don't know, some of the sample data changes or I add more data in. If I use that if statement, and you don't have to use the if statement on the Excel homework I'll post today, you can simply kind of look and state the p-value is less than alpha, so I reject here. It's not here, so I fail to reject. Or in the Excel file, you can, kind of build in this if statement if you want to start playing around with that a little bit. And all we're going to do is say, okay, if the absolute value of the test statistic, so ABS, absolute value of the test statistic, is greater than the absolute value of my critical value, if that's true, I know I should be rejecting. So comma, if that's true, put in the word reject. Comma, if that's false, put in the word fail, or you could even say fail to reject if you really wanted to. Okay? So if I copy this down, what's going to happen is, okay, so I reject That's what I said using the p-value approach as well, so everything's good. Looks like everything's good here, but notice I'm not using any test statistic because my cell reference is updating. I don't want it to. I wanted the cell reference on my critical value to update so I could make the rejection decision at different levels of alpha. But I'm using the same test statistic. So if I go here, the cell reference for my test statistic, I should have that frozen so that when I get down, when I copy this down, okay, I'm still comparing the absolute value of the test statistic to the absolute value of my critical value. And I'll see here, I made the same rejection decisions. Okay. So critical value approach, here was just the eyeball p-value approach that we did over here, but same decisions. Any questions on that? Want to see something again? Not understanding something really good? Yeah. This? I'll close this out for a second. So what we kind of determined here is we can reject the assumed true difference of 0, or sorry, we can reject the null hypothesis here that this difference is greater than or equal to 0 based off the sample evidence we found. Okay? So I can reject it at the 90% level. Now, what if instead I want to say, okay, well, I know I can reject the null hypothesis that it's greater than or equal to 0 because I found pretty, if I look at the sample difference here, it's about negative 0.1. Right? There's almost a 10% kind of difference here. So can I reject, not just is it greater than or equal to 0, but can I reject that it's greater than or equal to, I don't know, negative 0.02? So basically here, what it would allow me to say is, not only can I say that the difference isn't positive, I can tell you it's not positive and the difference isn't as small as 0.02, right? It's something larger than that. Well, if I hit enter here, okay, I can still reject it at that. Actually, did I even have that? No. So I need to change both of these. So I change these, my null alternative hypothesis. Okay, now I would kind of fail to reject, right? I can't really reject values that are much kind of lower than 0. 0 is kind of my stopping point. I might be able to do like 0.01. We'll say, okay, I could reject that the difference is greater than or equal to 0.01, right? But I couldn't do it for 0.02. Now, I'm never going to expect you guys to do examples like that, but you can kind of tell like this allows me to even make even broader statements, not just, is proportion of schools in the South that have more female students less than the proportion, or sorry, greater than the proportion of schools in the Midwest that have more female students. Not only can I say that, I can say that it's at least this much greater or at least this much less. But like I said, I'll kind of keep that out of the expectations of this class in terms of the homeworks and the exam. But I do want you to know that you could start to do that. For us, we're just going to keep these at 0. Okay. I also just kind of point out something here. It's pretty difficult with proportions to be able to reject this difference sometimes. So notice here, like, what's the greatest difference I could find between two sample proportions? Well, what's the lowest a sample proportion could be? 0. What's the highest a sample proportion could be? 1. So even if I found that every school in the South had more female than male students and every school in the Midwest had the reverse, more male than female, I still only see a difference of 1. So the fact that I saw a difference here of 0.1, well, that's like a tenth of as large as I could ever see the difference be. So I found a pretty large difference here. But even given that sample difference I found of what, negative 0.1 almost, it still results in that I actually can't reject that assumed true difference of 0 at the 95 and 99% levels. So even more so with proportions, I can't change the sample proportions I see. That just is what it is from the data, right? But what I can do is try to get as high of a sample size as possible. All right, so same sort of principles apply as when we're doing one population stuff. Let's say instead I found these exact same values, but I don't know, let's say I had 500 schools from each, right? Well, notice that starts to, well, where did I have it? Here it is. that starts to change that standard deviation of my difference in sample portions. It drove it down quite a bit, which meant seeing the same sample difference became more standard deviations away from that assumed true value of 0, that assumed true difference of 0, which decreased the p-value, e to the -5. This p-value is essentially 0 now, and now I can reject at every level, right? So one thing that we can try to influence when we're going out and gathering data is try to get as high of a sample size as possible, because it allows me to be more likely to be able to make rejections. Now, also notice the handiness of these if statements. Anytime I was changing something, well, these don't change, right? I just typed a letter in there. So I have to go back through, now compare the new p-value, retype things in. If I use these if statements in practice, if I wanted to change anything, it kind of automatically updates them. So I'll get this, actually, let me take it back to where we had the actual sample sizes so that when I post this, it doesn't look too weird. So I'll post this up on Canvas and call it like in-class work. Using this South worksheet should get you through about, or be a really good template for, about 2/3 of that Excel assignment that I'll also post once I get back to my office, okay? I'll also put up an online quiz for today. Should be kind of a simple question, or kind of one question, but it is going to be a problem where you have to kind of work out one of these hypothesis tests or work out one of these confidence interval examples. Start to try to get some practice with them. Other than that, what we will do on Thursday, and we might get out a little bit early on Thursday. I'm trying to kind of keep my sections all together, and we got a study day this week in my other sections. So we will start on difference in sample means. Here you go. When I don't know the population variance. Well, we only have sample variances now, so just like with one population, we're going to be looking at the student T again, right? But it shouldn't be a whole lot of new stuff. Shouldn't be a whole lot of new stuff. So we'll do that. We'll work through some Excel examples with that type of problem. And that will leave us with really the only thing left the rest of the semester to talk about is matched pairs and linear regression. Okay. Any questions for me before we get out of here? So 2 weeks from today. So Tuesday, whatever. I'll add 14 so that, wait, it doesn't sound right. What was yesterday? 12. Yeah, I think I'll have it set 2 weeks from today. So yeah, that's right. 2 weeks from today. So the 5th Excel and Connect, I kind of already mentioned, are going to eventually overlap the current Connect and Excel, right? So there's going to be some overlapping, kind of like Connect 4 won't be due yet, but Connect 5 has been assigned, right? And this was because if you've done all, right, you only have to do 4 out of the 5. If you're happy with your grade, if you just skipped one of the last ones, it's a 0, it gets dropped, right? So we'll probably get that next Connect and Excel assigned towards the end of next week. So I would personally suggest, also because I think it'll be good study for the exam, to do these 4th assignments. That way, if you do well, you can just kind of forget about the 5th one, right? Because if you're happy with your first 4, that 5th one will get dropped, right? I would suggest doing that, but the 5th assignment is a little bit shorter, a little bit maybe relatively. I don't know. I shouldn't say it's not gonna be easier for everybody, but it's for some people to be a little bit easier. So it's kind of up to you once both those are kind of assigned, kind of choosing which one you want to do there, since the lowest one will get dropped. Okay. Any other questions from me? All right. I will see you guys on Thursday.